So thank you very much for the nice introduction. And I also I want to say thank you for the invitation. I really appreciate having this opportunity. And I spent some time visiting the webpage of the math department in the university, and um, I can see that it's a really nice place, really great place, but I'm not there. In unusual situation. Anyway, okay. So yeah, but thank you. Okay, so I want to start off by giving some motivation. So so everybody can see my screen, okay? Yeah. Okay. All right. So we let G be a group, and we let A be an abelian group. Okay. So now we suppose that G acts on A by so this is a group action, but we assume that the group action is by group homomorphisms. Okay, so just to be explicit, we have a map from G cross A to A. This is the action map. So it takes a pair G comma A. This is, so little g is in the group G and little a is in the abelian group A, and this goes to G dot A. So this is how we write the action of G on A. And so just a quick reminder, for example, so if H is an element of G, since this is a group action, the action of G on H dot G, H dot A, this is the same thing as taking the product of G and H inside the group and letting that act on the element A. Okay, and so the fact that G acts on A by group homomorphisms means that so suppose B is in the abelian group, then this means that the action of G on A plus B inside the abelian group is equal to the action of G on A plus the action of G on B. And this sum, this is occurring inside of A. Okay, so when we have this structure, we say that A is a G module. Okay. So until I say otherwise, as we roll along, A will continue to be a G module. Okay. So just a quick example. So let's take the group ring on the group G over the integers. So if we let G act on itself by multiplication, then that makes the group ring into a G module. Okay. All right. So some notation. Let's let n be a natural number, so greater than or equal to 1. And we define G sub n to be, so this is the n-fold Cartesian product of copies of G. So this is G cross ellipsis crossed with G. So we have this n times. Okay, and now I want to define the following sets Gn comma A. Okay. What we mean by this is the set of all functions. So just functions, the set of functions from Gn into A. Okay, and it turns out that since A is an abelian group, this is an abelian group. Okay, so for every n greater than or equal to 1, this set has the structure of an abelian group, and the way that this works is as follows. Sorry, this always okay. So suppose f and h are functions from Gn into A. Okay, so we want to define f plus h, and so f plus h will be a function from Gn to A, and it's just defined pointwise. So if we have an element gamma in Gn, this maps to f plus h of gamma, and this is defined to be f of gamma plus h of gamma. Okay, and yeah, so we have these abelian groups defined pointwise. Okay.
Excuse me.
Yes.
So is this the category? Is that a category? The set of functions from Gn to A?
Is that set actually a category?
Yeah. Sorry.
Well,
that's okay.
No, I think here it's just an abelian group.
Well, okay, yeah, sure. So, okay.
Yeah, so one thing, what I mean here is I mean Hom in the category of sets from Gn to A, but I think you're asking if the abelian group can actually be enriched to be a category, and is that what you're? Yeah, I've never.
Kind of. Thank you for the benefit of the doubt, but yeah. Sorry.
Okay. No. And I can
see it's an abelian group. It's just like I because there's a lot going on. I thought it could be, but okay.
Yeah. So it is Hom in the category of sets, and one other thing I can say about this is another great way to view this is so as an abelian group, it's a direct sum of copies of A, where the indexing set is all of the elements in G sub n. So it's a direct sum. Yeah. Sorry, I can't hear you now.
Sorry, no, that's okay. I shouldn't interrupt. Yeah.
Okay. Okay. Sure. Yeah. Okay. So so here's what we do with these abelian groups. There is a cochain complex that has the following form, and I will say, when I'm done writing this down, I will quickly say what a cochain complex is. So there's a cochain complex that starts with A and goes to sets G comma A, and let's call this homomorph. So there's a group homomorphism here. Let's call it D upper 0, and maybe that looks a little strange. Let's write it as a subscript. Okay, so there's a group homomorphism D1 that goes to sets G2 comma A, and this we have infinitely many of these. So we have a homomorphism into sets Gn comma A, and then a homomorphism out of that, and this keeps on going. So this is D2, this is D sub n minus 1, and this is d sub n. So we have this infinite sequence of group homomorphisms. So each d sub I is a group homomorphism. Okay, and what makes it a cochain complex is the fact that for n greater than or equal to 1, every composition dn composed with d sub n minus 1 is just a zero homomorphism. Okay, so for yeah, so what we're saying here is that if we take this composition, it's just the homomorphism that sends everything in A to 0. Okay, if we take this composition, it again is the zero homomorphism. So every element in here goes to 0, and so on. Okay, okay. Oh, I should say I'm not going to say how these homomorphisms are defined. There's more than one way to do it. So for this talk, I'm just going to say that there are such group homomorphisms. Okay. Okay. So now I want to define a motivating object. So H upper N of G comma A. Okay, this is the group cohomology of G with coefficients in the discrete G module A. Okay, and I can just mention, you may have noticed that the action of G on A does not play a role in the definition of the abelian groups in the cochain complex, but it does play a role in the definition of the homomorphisms. Okay, so it is there. Okay, okay, so we have the group cohomology of G with coefficients in A, and I should say that in here is greater than or equal to 0. And this is defined to be the kernel of d sub n modded out by the image of d sub n minus 1. Okay, so what we do is we go to the nth spot. Okay, and we take the kernel. That is to say, we form the abelian group of all the elements that get sent to 0. Okay, and then we form the quotient group, where what we quotient out by is the image of the map that goes into this nth spot. Okay, and this condition is what tells us that the image is a subgroup of the kernel, and so this quotient group is defined. Okay, and so by definition, this quotient group is another. So we have another abelian group. Okay, so I want to say a little bit about the meaning of group cohomology, why it is interesting. So there's so the meaning of group cohomologies. So I just want to point out a few facts that say that this is an interesting collection of abelian groups. Okay, so let's look at the Zeroth cohomology group. Okay, it turns out that this is equal to A upper G. So what we mean by this is, so this is the abelian group of G fixed points. Okay, so just to be explicit, this is all the elements in A such that G dot A is equal to A for all G in the group. Okay, so it's the fixed points by the group. Okay, so I want to say something about the meaning of H1. Let's suppose that A. So for this point, let's suppose that A is a trivial G module. Okay, so what we mean by that is that the group action is trivial. So so for all A in the abelian group A, G dot A is equal to A for all G in the group. Okay, and actually I don't know why I put that in parentheses. This is actually the definition of this concept. Okay. Yeah, so the group acts by doing nothing at all. Okay. So in this case, H1 of G comma A is equal to the group of all group homomorphisms from G into A. Okay, so and the addition is defined pointwise, and because A is an abelian group, this group is an abelian group. Okay, so so H1 in this particular case is interesting, and let's go back to letting A be any G module. Okay, and we want to say something about what H2 is. Okay, so so here's a definition. So a group extension of G by A is a short exact sequence so it's a short exact sequence that has the form 0 to A to E to G to 1. Okay, and this is a short exact sequence in groups. Okay, so so on the ends we have the trivial group. Okay.
Okay.
Yeah. So here
as multiplication, that's okay.
So since A is an abelian group, here we're writing the trivial group additively, and then since G here need not be abelian, here we're writing it multiplicatively. But on the ends you have the both groups are the trivial group. Yeah. And okay, so
because of the compatibility of addition with multiplication, you can just do that, can you not?
I'm sorry, what?
Oh, sorry, I'm just getting the hang of this. Well, because addition and multiplication are compatible, I think you can just go from additive to multiplicative notation, perhaps.
Well, he has group homomorphisms, so he's imposing the compatibility.
Oh.
Yeah.
Thank you.
Yeah, so okay. Yeah, so we have 5 groups, and they are related by group homomorphisms, and at each spot we have exactness. So so just quickly, what that means is here we have a monomorphism. Here we have a surjection, and here the image of this map is equal to the kernel of this map, and And E in the middle there is just some group that makes this work. Okay, so so now here's a definition. Suppose we have two group extensions of G by A. Okay, so we have 0 to A to E1 to G to 1, and suppose we have another 0 to A to E2 to G to 1. Okay, and so these two group extensions are equivalent if we can do the following. Okay, so the requirement is that there's a group homomorphism from E1 to E2. Let's just call it phi. And this is an isomorphism, and it has the property that when we take the identity map on A and the identity map on G, then this diagram commutes. Okay, so so this is an equivalence. We have an equivalence relation on the collection of group extensions of G by A. Okay, and so here's a classical theorem. The second cohomology group of G with coefficients in A is isomorphic, and by isomorphic I just mean as sets. So we have a bijection here. Okay, is isomorphic to the set of equivalence classes of extensions of G by A. Okay, so that's some concrete meaning for the second cohomology group. Okay, so now what we want to do is to get closer to the real matter. So now we add a topology. We add a topology to G, and then we're going to retell the story. Okay, and basically it's the same story, but there's additional structure. So certain things get decorated in certain natural ways. So I want to say how that goes. Okay, so so let our group G. So now let G be a topological group. Okay, so and we assume that it is compact. Okay, Hausdorff. And totally disconnected. So totally disconnected. That just means that the only connected subspaces are the 1-point sets. So the connected components of this space are all of the 1-point sets. Okay, such a group is what is called a profinite group. Okay, and this has the consequence that G is isomorphic. Excuse me. So this has the consequence that G is isomorphic to the inverse limit over all the open normal subgroups of G mod n. Okay, so I should say a little bit about this. so I said isomorphism here. So this is a group. This is a group isomorphism, and this is also a homeomorphism. Okay. And okay, so this inverse limit is over all the open normal subgroups of G. And so one thing that means here is, so N is normal, so this is a group, okay? And then it turns out that because N is open, this is a finite discrete group. Okay, so so each one of these G mod N's is a finite group, and it naturally has the discrete topology. Okay, so so I'm saying that this isomorphism is also a homeomorphism. So so these quotient groups have the discrete topology, and then you take the Cartesian product of all of them, you give that the product topology, and then you the inverse limit is a certain subset of that, and you give that the subspace topology. So that's the topology on the right hand side. Okay, so
Okay, so that's an inverse limit.
yes.
Okay.
Yes. Yeah, so it's, if you're not familiar with those, let me just say it's kind of a generalization of an intersection.
Okay, and so open normal, you did say open normal, but okay.
Yeah, so it's an inverse limit over the collection of open normal subgroups of G. Yes.
Okay, thank you.
Yes, sure. An example is ZP, the p-adic integers for any prime P. Okay, so that's a topological group that has all of these properties that I've been talking about. Okay, so we've added a topology to G. So this means that we need to add some structure to A. So now we give A the discrete topology, and we require that the action map. Okay, so A here is still a G module. We give it the discrete topology, and we're assuming that the following is true. So let's look at the action map. Okay, A is discrete, so A here is discrete. G has a topology. Okay, and then you give G cross A the product topology. Okay, and the requirement is that with respect to these topologies, the action map is continuous. Okay, so so when that happens, we say that then A is a discrete G module. Okay, so from now on, whenever I write A, we have a discrete G module. Okay, so let's continue retelling the story, but adding in the needed decorations. So once again, we let N be greater than or equal to 1, and so earlier we considered that abelian group. So the analog that we want to consider now is the following. Let's look at map sub C Gn comma A. So this is the set of all continuous functions from Gn into A. Okay, so so we're just adding structure, adding one structural requirement, and that is that the functions that we consider be continuous. Okay, and again, this is an abelian group. Okay, and the definition is the same. That the addition is defined pointwise, just like it was before. Okay, so let's continue retelling the story with decoration. Okay, so once again, there is a cochain complex that has the form. Whoa, sorry. Okay, sorry about that. So there is a cochain complex that starts with A as before and goes to, so I'm going to reuse I'm going to call the maps the same thing. So D0 goes to map sub C G comma A. We have a homomorphism out of that into map sub C G squared comma A. And this pattern persists as before. So we have D sub n minus 1. We have map sub C G n comma A. And this homomorphism, again, we call D sub n. Okay, and this is a cochain complex. So we have these abelian groups. They're connected by group homomorphisms, and it's a cochain complex. So successive compositions give the zero homomorphism. This guy ought to end somewhere here, but anyway, okay. So we do what we did before. So since we have a cochain complex, we can make the following definition: H upper n sub C G comma A. Okay, this is defined to be the continuous cohomology of G with coefficients in A, and the definition is analogous to the earlier definition. So we go to the n spot and we take the kernel and then we quotient that out by the image. Okay, so this is the continuous cohomology. Okay, so so I want to say something about its meaning. So its meaning, let me quickly summarize by saying it's as before. Okay, so it's as before with natural tweaks. So I want to quickly go over what that means. So in degree 0, so G is our profinite group. A is now a discrete G module, and I can put a C there. So for the zeroth continuous cohomology group, and the exact what you had before is again true. Okay, so the exact same, I don't know why. Sorry, I'm not sure what is going on. Okay. Yeah, so you have the exact same result that you had before. Okay. In degree 1, let's take our discrete G module. Let's assume that the action is trivial, and we put a C here. Okay, and when we do that, we have the exact same result that we had before, except now we need to say continuous group homomorphisms. So H1 is the group of all continuous group homomorphisms from G to A. Okay, and so in degree 2, we want to put a C there, and here's how we do this. So we have our discrete G module A. We require this to be finite. Okay, and then we have the earlier definition, we have a short exact sequence, but this short exact sequence is now in profinite groups. Okay, so so all of these homomorphisms are required to be continuous. Okay, and E is a profinite group. Okay, so we only need to add the requirement that the homomorphisms are continuous and that E is profinite. Okay, and then to the concept of equivalence down here, we only need to add the requirement that phi be a continuous, that phi be continuous. Okay, so so when we do that, this is valid for continuous group cohomology. Okay, so all right. Okay, so so I want to let's see. I'm getting kind of short on time. So let's let n be greater than or equal to 0. Okay, and let's look at hn sub c of g comma a. Okay, so we can write this as the nth cohomology of the above cochain complex, but let's write it like this. Okay, so this is ranging over 0, 1, 2, 3, etc. Okay, and let's close this up. So we're taking the nth cohomology of this cochain complex. It turns out that this is the limit over. So we're going to take the. So we're often going to be looking at letting n vary over all the open normal subgroups of G. Okay, so I'm just going to, for shorthand, I'm just going to write that as n. Okay, so we take a limit over the n's of G mod n, and we have star. Okay, and this A is a union over the n's of the fixed points. Okay, so we take the fixed points of A by n. Okay, now it turns out, so we have a limit in the source, and we have this union, which is a colimit in the target. So it turns out that we can pull that outside, and we get the colimit over the n's of map C G mod n star A upper n. Okay. Now, G mod n is a finite discrete group. So this is actually just sets G mod n star A n. Okay. And this colimit, this is it's a filtered colimit, so it you can pull it outside the cohomology group. So this is the colimit over the n's of hn, and then we have sets G mod n star a n. Okay, and it turns out that this is exactly the nth cohomology group of the finite group G mod n with coefficients in an. Okay, so okay, so we have this isomorphism here, and now what I want to do is suppose that A is a trivial G module. Okay, so if A is a trivial G module, then AN is just equal to A for all n. Okay, and so what that gives us is that the for every n greater than or equal to 0, the nth continuous cohomology of G with coefficients in A is isomorphic to the colimit over the n's of the nth cohomology group of G mod n with coefficients in A. Okay, so this is a classical theorem, so what I would like to talk about, in the remaining time is we would like to have a version of this for the setting of spectra. Okay, and so I need to define a few things. So we still have our profinite group G, okay, and so we want an analog of the concept of discrete G module in the setting of spectra, and here is that analog. So we make the following definition: a discrete G spectrum X is a collection x0, x1, x2, ellipsis, xn, ellipsis of pointed spaces, but these pointed spaces are discrete G spaces. Okay, so they are pointed spaces. They have an action by G. You give them the discrete topology, and then the action map is continuous in that case. Okay, and I forgot something. I need to add the following. They have pointed G equivariant. So there are pointed G equivariant maps, S1 smash xn to xn plus 1. And here n is greater than or equal to 0. Okay, so one thing, the source and target, both you give them, so naturally they have the, so in this setting, they naturally have the discrete topology, and so this map is automatically continuous. So you let G act on S1 trivially, okay? Saying that the map is G equivariant means that this map of spaces preserves the group action, okay? So f of G, say Z is equal to G acting on f of Z. So the group action is preserved. And the smash product here, this is like it's a pointed version of the Cartesian product, okay? I should say here that I've given a kind of a rough definition of the concept of discrete G spectrum. If I were to define this in a fully precise way, we would be working with the category of symmetric spectra, which use pointed simplicial sets. Okay, but that's a little heavy for now. But yeah, to do this properly, you want to use symmetric spectra of simplicial sets. Okay, because of time, let me just say that there are maps. So let me just quickly, there are maps in this category. Okay, so if X and Y are discrete G spectra, this is a collection of maps Xn to Yn. Okay, and these maps are required to be G equivariant. and they commute in the, so they're compatible with these structure maps. Okay, so this this category has morphisms. Okay, and well, so we have morphisms between these objects, and so this gives a category. And let's write this category as SP sub G. Okay. All right. So a map, we say that a map is an equivalence if the induced map on stable homotopy groups is always an isomorphism. So, and I say a map, I mean, let me just say, we mean this map. Okay, so the map X to Y. Okay, so we have what we call an equivalence. If the induced map on stable homotopy groups is an isomorphism for all n in Z. Okay, so this is like our concept of isomorphism in the setting of discrete G spectra. Okay, so there is a functor which goes from the category of discrete G spectra to spectra. Okay, and I just want to say by spectra, what I mean is you take the earlier definition and you just omit everything having to do with the G action. Okay, so a spectrum, you take a collection of pointed spaces. Okay, and we have pointed maps. We drop the G equivariance, so these pointed maps look the same way. Okay, and these, so for discrete G spectra, these maps are G equivariant, but for spectra, you just drop that requirement. Okay, so that's a rough definition of what spectra, what the category of spectra is. Okay, so this functor takes a discrete G spectrum and sends it to the fixed point spectrum. Okay, and this fixed point spectrum, what we mean by this is the spectrum that is the collection of spaces x0, and then you take the G fixed points, and then you take the G fixed points of x1, the G fixed points of x2, etc. Okay, so we have this functor. Okay, and so there is a, well, let me just okay, I'm getting short on time. So let me say the following. So this, so back in the algebraic setting, this functor is a right adjoint from G modules to abelian groups. Okay, and now in the setting of spectra, this functor is what we call it's a right adjoint again, and it's what we call a right Quillen functor. Okay, so there's a model category structure here, and this right adjoint behaves well with respect to special maps that are called fibrations, and so it behaves well with respect to fibrant objects also. Okay, so let me just say that, so just quickly, this functor has nice properties. Okay, so here's a definition. Let X be any discrete G spectrum. Okay, so so you can always do the following. Okay, you can form a map from X to an object called X sub FG. This morphism is in the category of discrete G spectra. This is an equivalence, okay, and this object is fibrant, okay, in that category. So so that means that this right Quillen functor behaves very nicely on it, okay? And so we make the following definition. XHG, this is what we call the homotopy fixed point spectrum. And the definition of this is X sub FG. So you take this guy, and then you take the G fixed points of it, okay? And notice that if we're flexible with our notation, this is the same thing as the zeroth continuous cohomology group of G with coefficients in this discrete G spectrum, okay? So, right, the zeroth continuous cohomology group is just the fixed points, and we have that here too if we're flexible with our coefficients, okay? And often, so I don't have time to talk about the hypotheses that are needed, but they are often satisfied. There is a spectral sequence whose abutment is the stable homotopy groups of the homotopy fixed point spectrum. And the E2 term, so the E2 term of this spectral sequence is the continuous cohomology of G with coefficients in the stable homotopy groups of G. I'm sorry, the stable homotopy groups of X, okay? So for these reasons and more that are related to this, we think of this as an analog of the continuous cohomology of G with coefficients in A. Okay, so so I have a few minutes left for to state the real goal. Okay, so let's let X have trivial G action. Okay, so just to be clear, take any discrete G space X sub n, take an element X in that, and the assumption here is that the action of G on that element is just X, okay? There is always a map that has the following form. We take a colimit over n, okay, and we have X H G mod n, okay, and this goes to, a certain object. I don't want to say what that object is, but the important thing about it is equivalent to the homotopy fixed point spectrum, okay? So, so I want to make a few comments about this map. So for every n, our assumption on X means that X is equal to the n fixed points, okay? So, so this spectrum, it's natural to think of it as having a G mod n action, okay? Well, since the original action on X is trivial, this action is trivial, okay? But it does have a G mod n action, and so we can form this homotopy fixed point spectrum. So this is the homotopy fixed point spectrum with respect to the trivial G mod n action, okay? So I just want to point out here that we have a map. So this is our analog of the continuous cohomology of G with coefficients in A, and then the source of this map is our analog of the cohomology of G mod n with coefficients in our trivial G module A, okay? And classically, we always have an isomorphism here, okay? And what we're interested in is an analog of this in the setting of spectra. And so the question is when is phi an equivalence? Okay, and so I've been able to show that this is an equivalence in a few cases. It's always an equivalence when G is finite. That's not very exciting to show. It's always an equivalence when pi t of x is equal to 0 for all t greater than or equal to some fixed integer. Okay, so the homotopy groups, the stable homotopy groups are bounded above. And then the third case, so let's see. Okay, I guess I should just say it. The third case is we have a collection of, so this is a subcollection of the ends, okay? It's required to be cofinal, okay? And the requirement is that for each u and every t in z, the continuous cohomology groups of u with coefficients in the stable homotopy groups of x, this is equal to 0 for all s greater than 0. Okay, and so these hypotheses are pretty strong, and so they have additional consequences. They imply that you have this equivalence for every u, and they also imply that you have this equivalence for every u. Okay, and so the conditions here are pretty strong, but I've been able to come up with some examples that I think are pretty interesting. But I suppose I should stop. Yeah, it's 4:28. I think I should stop. But yeah, but feel free to ask questions.
All right, let's unmute ourselves and thank Daniel.
Well,
Thank you.
thank you. Thanks.
Are there any questions?
Martin, I have a question, maybe more than one. Yeah, so thanks a lot for the lecture. I was wondering, so when you started your lecture, you had A as an abelian group.
Yes.
And later on, it looked like A needed to have a topology because you began to talk about continuous homomorphisms. So, so I began to think of you know, what would be nice groups, nice abelian groups to be considering, and you know, I was thinking of the torus. I was also thinking I'm in operator theory, so I was thinking like the, you know, a C-star algebra as an additive abelian group, and then later on you went on to stable homotopy groups, and so I was just wondering, I don't know much about stable homotopy groups. Do they, first of all, are they abelian, and do they come with a sort of a natural topology?
So stable homotopy groups so they're graded over the integer. So given a spectrum, you can take the stable homotopy groups of the spectrum, and they are always abelian groups. But in general, you don't think of stable homotopy groups as having a topology. One thing, if you take an arbitrary spectrum, you can say, well, let's let G act on it trivially. And so then you take the stable homotopy groups, and then because, so the induced action on the stable homotopy groups is trivial. And so you can just give it the discrete topology and regard it as a discrete G module. So just for free, for free, it has the discrete topology. Good. But I think, so I would like to write an example, but I think I'm not screen sharing, so I need a second. Okay. Yeah, it stopped screen sharing because I wasn't writing on the screen. But okay, can you see my screen now?
Yes.
Okay.
Yeah, we can.
Okay, so there are cases where, so En is a certain spectrum, and it has stable homotopy groups. And so what I want to do is I want to give you an example of stable homotopy groups that have an interesting topology on them. So so it turns out that the stable homotopy groups here are, you take the Witt vectors of the field with p to the n elements, and then we have a completed power series ring in n-1 variables. And this is all in degree 0. And then we add an element u, which has degree -2. Okay, so so these are the stable homotopy groups of this is what's called the Lubin-Tate spectrum. In homotopy theory, it's a really important spectrum. And in each degree, the homotopy groups are profinite. So actually profinite commutative rings. So yeah, so this topology arises in a natural way, and so it's not just an abelian group, but it turns out it's a commutative ring, and these commutative rings are profinite. So they are inverse limits of finite discrete rings.
Yeah.
I don't know if that answered your question, but
yeah, actually it does. Like I've done some work in C-star algebra theory with it's really similar in flavor, where we're taking inverse limits of, well, what would be equivalent to inverse, topologically, they're inverse limits of the stone-check compactifications of dense open sets, sort of an algebraic analog of that.
Okay.
And so this is very strongly similar in flavor to what we do in C-star algebra.
I see. One thing I could mention is the continuous cohomology groups that I've talked about. So what I was talking about today, the coefficients they always had the discrete topology, but you can just let them be a topological abelian group that's Hausdorff. And actually in this setting, especially when you're talking about the spectrum En, you're often interested in continuous cohomology groups where the coefficients are profinite. So and so then you have, for example, you would have inverse limits of the kinds of continuous cohomology groups that I was talking about in my talk.
Yeah. Okay. Great.
So then Mittag-Leffler conditions come up, and I know in some work that I've done on this, I looked at a paper by Claude Schocket. Is that, am I saying it?
That's how he goes. Yeah. He's probably one of the most. He's the one person more than any other person who bridges algebraic topology and C-star algebras.
I see. Yeah, his. Yeah, I've looked at a little bit of his work, and there is one construction he made that was helpful for the dissertation of my PhD student a few years ago.
Okay. Yeah. Good. Thanks so much, Daniel.
Okay, thank you.
All right, that's officially all the time we have. So let's unmute ourselves and thank Daniel again.
Okay. Thank you.
Thank you all for
everybody.
coming.
Thank you.
For those who would like to talk shop, maybe casually ask a few more questions, you can stick around for a few more minutes, I think.
And that sounds great. Sounds
Great. All right.
Thank you.
Thank you. Bye.